What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we have a challenge lab for you. It's an experimental design question based on our fictional officer, Officer P. Hicks. And this officer makes a claim related to stopping distance. Cars, trucks, vehicles that are driving down the road slam on the brakes and skid to a stop. We are not just talking about tires rolling, we are talking about tires sliding, kinetic friction on the road. And this officer makes a claim. This officer's claim is that the relationship between distance and velocity, this is stopping distance, this is velocity. The officer claims that stopping distance is going to be equal to some factor related to the coefficient of friction, some factor, some constant 1 over a. The stopping distance is equal to that factor times the speed of the car, meaning that as the car speeds up, the stopping distance will increase. And to me, that makes good sense. If I'm going faster, it's going to take me a longer time to stop. But our job, we have been tasked with constructing an experiment in the classroom that will either support or refute Dr. P. Hicks's proposal for this equation. So here's what we have. In the classroom, we're thinking to ourselves, all right, I need to obviously have some way to measure speed. I need something to measure distance. So I've got my photo gate right here. I've got my meter stick right here for both speed and distance respectively. I've also got a track that I can use, and I've got a car that I have taped the wheels on. And the reason I tape the wheels on it is so that it simulates kinetic friction. If the car's tires are going to roll, the rolling friction is very, very different than the sliding friction. And P. Hicks is talking about the sliding friction as we screech to a stop. So here is our setup. I've got a track, and what I need to do is determine the distance this car will stop over a certain period of time, right? Like I'm not going to measure time, but I'm able to then kind of move this car or push this car down the track. That was not a good push. But I can push this car down the track and determine, okay, if it moved half of a meter, how fast was it going in order for it to take half a meter to stop? So basically what we've decided to do in class is that we will set our photo gate on the track like so, and we'll measure from the final laser on the photo gate, and we will just send this car down the track with varying speeds and measure the stopping distance. So in this example, we see about a half meter of distance covered, and we see a speed of 1.37 meters per second. So let's go ahead and add this to our data, see if it goes somewhere. 0.54 meters is actually where it ended up. And 1.31 meters per second is what came out of the photo gate. You can see it right there, 1.37. And again, we got close to 54, whatever it is on there. So this is our data. So I've done this lab in class. I've been taking some data here before the video started, and these are the numbers I came up with. Now, they're all obviously out of order because all I'm doing is just flicking the car down the track and measuring different distances. So I can't really control what numbers come out except for how hard I'm pushing the car down the track. So I did it a bunch of times. I've got probably 8 to 10 data points up there. Go ahead and use that data to generate a graph. Now, when I do this, we're going to go see kind of what the relationship is here. Okay, so that's your task. Your task is to go figure out what this relationship is, to go graph this data. And if I'm going to graph this data, it looks like distance is going to be my y variable, and speed is going to be my x variable based on the equation that P. Hicks has here. Okay, now I have not looked at this data. I have not graphed this data, but I want you to. I want you to go look at it. I want you to go graph it. I want you to do those things. After you've graphed it, I want you to come on back. So pause this video right here, go graph your data, go linearize your data, and then come on back and we'll analyze it together. So pause the video. Don't cheat. Don't cheat. All right. Hopefully you've graphed the data. Hopefully you've linearized it. If not, you're a liar. Go graph your data. Okay. Here's what I get. When I see this, what I end up getting is a relationship that looks like this. This is the data that we get between distance and velocity. So it is not, in fact, a linear relationship. So Officer P. Hicks is not correct with this explanation. Was P. Hicks right that as velocity goes up, the stopping distance will also go up? You betcha. That's what I see here, but not in the way that they hypothesized. So when I go ahead to linearize this data, if I want to linearize this data, I had better have squared speed. And when I do this, I get a linear relationship looking or a good linear relationship in which the stopping distance is related to speed, but it's related to speed squared. And what this means is that if I'm going twice as fast, it's going to take me 4 times the distance to screech to a stop. And as we think about the winter months coming along and the roads getting icy here in the Midwest, we want to keep that in consideration as we obey speed limit signs. We drive more slowly when snow hits the ground, when it's nighttime and that water on the road starts to freeze because the sun has gone down. These are all things you want to consider, is that, if you're going twice as fast, the speed limit says 25 and you're going 50, or heck, it says 25 and you're even going 35 or 40, you're going to really increase the stopping distance you need to bring your car to a stop, especially on icy roads where that coefficient of friction is so small. Okay? So, our first answer is no. P. Hicks, you're not right. This is not the relationship. Speed goes up, distance goes up. We agree with you there, but that's not exactly the relationship we have here. So then I ask you, well, go ahead and find me an equation for this. And I hope a lot of you said, you know what, I've seen this distance and velocity squared thing before back in kinematics. In kinematics, we had an equation where the final velocity is equal to the initial velocity squared plus 2a delta x. This is a relationship that came up with this relationship. Velocity squared is related to the displacement of something. These are very closely related. One of these we have used kind of energy concepts for, and the other one we did with kinematics through graphing and taking data that way. We've seen this relationship before. This isn't a new thing for us. We see a constant acceleration due to the force of friction. We have an equation from kinematics. This is all kind of like coming full circle. Remember, energy is not a unit where we are learning new physics. It's just a different lens by which we can solve physics problems. We've done kinematics, we've done forces, we've done circles, and now we're going to use energy to observe and study and understand physical phenomenon. Okay? So as I walk through some of these questions back here, I want to go ahead and use energy to come up with an equation. This is a great stopping distance equation for me if I know the acceleration of the car. If I don't know the acceleration of the car, this becomes rather complicated. Now I could use forces and I could use an F-net equation for my system, go ahead and figure out what the acceleration of the car is, and then come back and use kinematics. That's fine. That's totally reasonable. I can also, though, use a work energy theorem. So let's go ahead and first start with a picture of what happened here. Now that we have seen that this relationship is a squared relationship, let's go ahead and try to come up with an equation for it. So this comes from the car that is moving this way. And the force is on the car. Obviously, the car has a weight. There is a support force from the ground called the normal force. And then as it moves to the right, there's a force of kinetic friction back to the left. These are the forces acting on it. And again, you could use F-net equals ma. Go solve this because I know the force of friction. I'm not sure what the coefficient of friction is. This would be challenging to figure out, but I could probably go back and look at previous labs and find out what the coefficient is between tape and track because we've done that before. But in this case, I want to use the work energy theorem. I'm being asked to use the work energy theorem. Let's use the work energy theorem. So, work energy theorem basically states that we have initial energy. That initial energy changes, either increases or decreases based on work, and then ends up being equal to whatever my final energy is in my system. And because the car is the only object present here, it's not changing heights, there's no springs, we're going to say the car is my system. So I'm going to kind of write that over here just to keep track of the car as my system. And let's think, initially is the car moving? And a lot of us want to say, well, no, Mr. Gustin, the car is not moving initially because guess what? When I put the car on the track, it's not moving. But this is not where my data began. My data did not begin with the car at rest. The data began as soon as I gave that car a push. So, is the car moving initially? Yes, it has to be moving. That's how I get a stopping distance. It has to be moving to be stopping. So, That's what I'm going to say. Initially, the car has kinetic energy stored in it. Is there work done? Ask yourself the question, is there an outside force acting on the car? And the answer is, let's look at my FBD. It looks like there's kinetic friction. So there is work done by the force of friction, kinetic. How much work is done? Well, once the car finally comes to a stop somewhere down at the edge of the track, is there any kinetic energy in the car? Is there any gravitational potential in the car? Is there any spring energy in the car? And the answer is no. The car alone isn't moving. It's not a spring. It's not loaded up. And it's not creating its own attractive gravity. Like, that's not happening. So all of that work by friction has removed or dissipated all of my kinetic energy. So this is my expression. I start with kinetic energy in the car. There's obviously an outside force by friction done, and I end up with 0 joules. And I'm asked to go ahead and find an equation for stopping distance in terms of some variables, in terms of variables that are here. So let's go ahead and start plugging those variables in. Kinetic energy is always 1/2 mv squared. The work done by friction is going to be the force of friction kinetic times that distance times cosine of theta. And I notice that I'm moving to the right and the force is to the left. This angle between those two vectors is going to be 180 degrees. So I'm going to go ahead and remove cosine theta. I know because they're in opposite directions that this work is removing energy from my system. So I throw a negative sign in there, make it a minus. Force of friction, I can kind of sidebar this. If I remember, force of friction equals mu times Fn. And in this case, that's going to be mu times Fg or mu mg. That's a great substitution for us to make when the normal force and the weight force are equivalent, like they are in this scenario. So I end up with 1/2 mv squared minus the force of friction, which is mu mg times d. This ends up being equal to 0, and I want to find an equation for distance. So I do some algebra. I'm going to bring this sucker over here. I see that distance ends up being equal to mv squared over mu mg times d. Can't forget to multiply this by 2. My masses cancel out, and I find that the stopping distance is equal to v squared over 2 mu g. This ends up being, if I do the algebra correctly, and I believe that I have, mgd, yep. This ends up being the equation for stopping distance. So was P. Hicks right? Distance equals 1 over some constant, and that constant is 2 mu g times v squared. This is my equation. Now 2 is a constant, mu is a constant for certain for 2 specific surfaces. G is a constant. Is he right? He was thinking it was v, but we end up knowing it's actually v squared. So no, they were not right. In fact, this is the appropriate equation. That is the appropriate relationship, and we can go ahead and use our energy or our work energy theorem to solve an equation that refutes, slightly supports, but refutes the idea that distance and speed are linearly related. They are related in a squared fashion. Okay? So given this equation, given this graph, given this set of data and this understanding, I hope you now have the tools to go finish up the analysis questions. As always, if you have questions, drop in the comments, send me an email, or ask me in class. Until next time, see ya!